Bueno, pues buenas tardes, sean bienvenidos nuevamente. Continuamos con nuestra serie de ponentes. En esta ocasión tenemos a Jessica Torres-Soto, quien es reciente graduada de la Universidad de Stanford y ella hizo trabajo muy interesante sobre la detección de señales electrofisiológicas relacionadas con ritmos del corazón. Actualmente ella está trabajando en el sector de la industria y pues nada, para mí es un honor y un gran gusto tener a Jessica aquí con nosotros. Así que únenseme para recibirla con un buen aplauso. Jessica, welcome. The floor is yours.
So I'm going to share my screen and then hopefully it's the right screen. One moment. Okay, let's see. Which one can you see?
We are seeing the presenter view.
How about now?
Now we see the one we are supposed to see.
Okay, great. Okay, so hi everyone. I'm going to be giving you the kind of breakdown of a portion of my PhD today regarding the paper that was sent out. But before that, I'm going to try and set the context a little bit more. We can make this as interactive as you guys like. So if you have questions, feel free to speak up. I do have a list of your questions all in a slide at the end. But if anything else comes up, we can either wait to the end or ask me when it comes to mind. But my PhD, I just graduated in June 2021, and my PhD was focused on machine learning methods for the prediction of cardiovascular disease. And so I'm very interested in cardiovascular disease, mostly because I have personal ties and a lot of connections to individuals, both within my family and close friends that suffer from cardiovascular disease. And it's well known that cardiovascular disease is the #1 cause of death globally. And it's estimated that around 17.9 million people a year die from cardiovascular disease, and it represents around 31% of the total global deaths. So it really is not only just a personal thing that I'm interested in, but it really is a global health issue when we think about it on a larger basis. And so let's see. Okay. So when we think about the context of cardiovascular disease, at least within the US, this is kind of a breakdown of what individuals, Americans, die most commonly of. And so we do see that heart disease is ranked #1 with cancer a close second. But when we talk about the media and how we portray what interests individuals, we see that media and searches and what people look for through Google searches actually focus more on cancer. I'm sure if you kind of did a search, if you had some issues and you plug it into Google, it's going to probably tell you that you have some type of cancer, right? That's like the big joke. And so the funny thing is that's actually disproportional to what most Americans die from. We do know that heart disease beats cancer just by a little bit, but when we talk about searches, more people are more interested in what cancer has than heart disease, which I think is kind of a shame given that a lot of people suffer from heart-related issues. So the point that I'm trying to make is that there's just a general significant disconnect between what people are worried that they might die of and what they actually do. So it's critical as a scientist to really give awareness to really what the impacts of taking care of your heart might do on your long-term health and longevity. So like I said earlier, the intersection of cardiology and machine learning is really where I focused my graduate career. And when we talk about machine learning, it sometimes can be a very broad kind of overview where people will use the terms artificial intelligence or machine learning or deep learning. And this is generally how I like to think of the different subsets. We have artificial intelligence as a broad category. It encompasses a lot of different types of methods. Within that, we have a small section of machine learning, and then under that, deep learning. And this kind of gives you a high-level view of how I structure the methods. We all know that machine learning, specifically deep learning, really got its kind of fundamental status through vision and image recognition. So we have here an example of a dog, and then you want to classify that versus birds, sunsets, and other cats. So this is really where kind of the field started out. But as time has gone on, medical applications of this type of work has really exploded. Currently, there's FDA work looking at your eye retinas, different types of CT images, as well as skin, and in our instance, looking at your heart. So my PhD was broken up in two sections. The first one was remote monitoring, and that's the one I'm going to highlight today. But I did do substantial work in improving cardiovascular care within our hospitals in terms of the data that's collected there. So I won't be talking about that today, but I do have a paper up in archive that you guys can look up. I'm currently trying to get it through different rounds of revisions, but I'll be highlighting the work that's already published on the remote monitoring. Okay, so this one is going to highlight the paper Multitask Deep Learning for the Detection of Different Types of Cardiac Arrhythmias in Wearable Devices. So within the past probably 5 to 7 years, you're going to probably notice that the marketplace for consumer wearable devices has really exploded. You probably own like an Apple iWatch or some type of Fitbit, or you know someone who really uses it probably to track their steps, maybe their sleep quality. And it's really kind of the first time that has given individuals the ability to track their own movements in a non-biased way. And so this gives real-time feedback to individuals, perhaps when they want to set a certain goal on movement, whether or not they're actually meeting that movement goal. As a researcher, I saw these types of devices when I was early in my PhD starting to become widely adopted. And I thought that it would be particularly compelling to apply this type of technology in a way that would be a little bit more actionable in terms of how can we quantify or characterize individuals at high risk of different type of cardiac events. And so the cardiac event for this paper that we focused on was atrial fibrillation. So you're going to see a plot of the normal heart on the left and atrial fibrillation on the right. And so what is atrial fibrillation, or AF, as I'll probably refer to it for most of the talk? It basically is an irregular and often rapid heart rate of the two top chambers of your heart that are really uncoordinated. This increases your risk of things like stroke, heart failure, and other types of heart-related issues. And a lot of the times in situations where people have atrial fibrillation, it's actually latent, so they don't know that they have it. This is on the bottom, what I pulled up is going to be kind of a cartoon of what is known as an ECG or electrocardiogram. This is going to be how, when you go to clinicians or some type of medical facility, how they kind of monitor your heart. And so this is going to monitor the electrical signals that are coming from your heart. I want you to pay attention to the yellow kind of circles that I denoted. You're going to notice on the left, we see normal spacings between these yellow peaks here and these yellow circles, where in the atrial fibrillation case right here on the right, we're going to see that there's abnormal spacings between them. And that's kind of indicative of that abnormal situation that's going on in the atriums that's pretty dangerous. So really the incentive to study AF is quite high, given that it's a huge risk factor for stroke, and that early detection of any type of AF may allow for interventions to happen to reduce that risk of stroke. And so we thought, what's the best way to do this in a way that can kind of, reach the masses? And with this adoption of wearable devices, we felt like it would be a proper way to do this. And so this is kind of where we wanted to blend cardiac monitoring and machine learning. So with the advancements of wearable technology, we can monitor individuals remotely, really from anywhere for a long period of time. And this technology is not new necessarily. It's known as photoplasmography or PPG. And how that works is it essentially emits in a light source. So in the back of maybe a watch or a Fitbit, depending on what type of wearable device you have, you're going to notice that there's a light. That light emits, that light source emits light, and then there's a photo detector that will kind of catch any reflective light that comes back, kind of shown right here in this figure. Now, the input data that we're going to get back from these devices are kind of denoted right here on the right, where you see representations of your cardiac cycle with these peaks and valleys. So as your heart pumps blood throughout your body, it's going to be able to see these ups and downs and these light absorption pattern in this way. The important thing to know—
I have one question.
Yeah.
The quality of the signal is the same in either hand, left and right? You have the same quality for the pulse signal?
Yeah, so in terms of if you're like right-handed or left-handed, that's a really good question. I don't think that there's going to be a huge difference in terms of when you're talking about signal quality. The way that I view signal quality is how clear of a signal it is in terms of peaks and valleys. There shouldn't be a huge discrepancy of a peak being much stronger on your right versus your left. If that was the case, that would be more indicative of one arm getting less blood flow than the other. And in most cases, it's going to be so minimal that it's not going to be picked up on this type of device.
Okay.
Good question. If anything, you might see a slight higher absorption on your dominant arm because it has, more muscle and kind of things like that. But that would be my best guess is minimal. Okay, so you're going to see these peaks and valleys from the wearable device. But it's really important to note that these signals that we pull from wearable devices are actually highly corrective and easily corrected. And so when we think about that, it makes intuitive sense. If you're wearing a device all day and maybe you talk with your hands like I do, or you're very active and you're moving a lot, it's going to be corrupted by noise. And so that true signal that we're hoping to get from the device is actually going to be convoluted with this movement that we may have. And so the signal that we pull from the device is going to be kind of a mixture of the two. And it's estimated that inaccurate heart rate estimations and misdetection of AF are really largely due to poor signal quality and not necessarily something else. And so this is why it was critical when I started looking at how can I create an algorithm to be able to detect AF. I found it was critical that we address signal quality properly. So there was some work in this realm when I started on talking about how do we use these signals to quantify whether or not they are good kind of medical grade. This was the one paper that talked about signal quality index, and they denoted that over time, if you were looking at a specific segment of signal, it's likely that signal quality or how well the signal quality is going to degrade. Well, this is a super critical amount of information because when we're looking at classifying AF, we can't look at just one single heartbeat. We're going to have to look over a series of time to see that pattern of whether or not that pattern looks regular or irregular. So a lot of these signal qualities estimations, we're looking at single beats, which would not necessarily apply in our situation in terms of looking at longer time frames. So I knew that we needed to kind of address longer timeframes rather than just single beat instances.
I'm sorry, can you repeat what unfit means here?
Unfit, so it's poor quality. So essentially in this situation, you'd want to see this nice peak and then as a slow degrade. In situations where, let's say it's an acceptable, so you can kind of tell that there's a peak